Okay, question 5, we have this IV characteristic, and we have to say why is this non-ohmic, and that's of course because we don't have a straight line through the origin. I is not directly proportional to V. That's the definition of an ohmic device. Okay, next one. So here we have X in series with a variable resistor, and we need to find the resistance. Okay, we know 20 milliamps is flowing through the whole circuit, so that means we have 20 milliamps flowing through everything, including X, and we can therefore go back to the graph and we can look up what is the potential difference across X given that current, and that looks like it's around 2.3 volts. So if we have 4 volts in total available and 2.3 is across X, then we know 1.7 volts has to be across R. They're in series, voltages add up in series, so we have 1.7 volts across R, and we can now work out the resistance because we know the voltage and the current, and resistance is per definition the ratio of the applied voltage to the current flowing, and we get around 85 ohms. Okay, the power dissipated in the whole circuit, pretty easy. We know the overall voltage, we know the overall current, so we have 4 volts times, should be times 0.02 amps, and we get this number of watts. Okay, potential divider, range that we can get. Well, we know when the slider S is all the way down at Q, then we have 0 potential difference across X, we have 0 current through it. Whereas if we slide it all the way up to P, then we have the full 4 volts across X. We have the full potential difference of 4 volts across X. So we can go back to our graph and see what we get. At 4 volts, we get 60 milliamperes of current flowing through X. So we're going to go from 0 to 60 milliamps. And we get the 60 milliamps when the slider S is at P. Okay, then we are now assuming that we have 20 milliamps through X and have to draw some conclusion about the overall power dissipated. Okay, so remember there's a main current that comes to S, which is sort of a junction, and then some current, the 20 milliamps, flows through X, but there is still a little bit of current that goes from S to Q. Some current, right, is going from S to Q. So the main current flowing into the junction at S has to be more than 20 milliamps. So we can first draw that conclusion that the main current coming into S has to be more than 20 milliamps because we have 20 milliamps going through X, and then we have some other current flowing from S to Q. So main current is greater than 20 milliamps, and that means overall we have a larger power dissipation because we still have 4 volts of total voltage available in the circuit, and if the main current is going to be bigger than 20 milliamps, then we have a larger power dissipation compared to the previous problem. So that is what we're going to write here. Hence the overall dissipated power will be greater than, sorry you can't see that, but I'm going to scroll up in a minute and you can see. So it's just P equals to VI again, where the V is still 4, but then we have a slightly larger main current compared to